Alright, so we're going to start on lesson 72 now. This is proportions in a right triangle, so we're going to get into some trig in this chapter. But before we do, we're just going to talk a little bit about right triangles. So any right triangle that we have, like ABC, triangle ABC here, which is a right triangle, it can be divided into two smaller right triangles. We did that just by drawing the altitude from the right angle. And when we go straight across, remember an altitude has the makes a right angle as well with the hypotenuse. So see, it has the big triangle, and then we divided it, and so now we have two smaller triangles, ADB and DBC. So there are three triangles now that we're talking about. And we can do that with any right triangle at all. And what's really interesting is that when we do that, all three of those right triangles are actually similar. So by drawing this one altitude, we've created two triangles, and those two little triangles are similar to the big triangle that we already had. So let's look at that a little bit further. So all three triangles are congruent. Here they are listed. ABC is the big one. Then we have the medium one, which is ADB, this one down here. And then we have BDC, the small one. And you can line up their angles, like all the right angles, of course, would be congruent to each other. So this angle, this big angle here, and then the other right angle as well. We can also compare the other two just by looking at the larger and the smaller. So the larger angle of triangle ABC would be angle C. Angle C, remember, big side, big angle. If you forget that, you know that it's across from the larger side, so C must be the bigger angle. Looking at this triangle ABD, we already have the right angle, but it looks like B would be bigger because it's across from the bigger side. And then in the small triangle, we have the right angle right here, and then across C would be the next biggest angle. So, and then we have the smallest angle, and those would all be the same as well. You can also set up their sides. You can look for the hypotenuse of the two triangles, the long leg and the short leg, and you just kind of look at each triangle individually and figure out where's the hypotenuse, where's the long leg, where's the short leg, and you can compare that to the big triangle where it's easy to see because all three of those triangles are going to be similar. There's actually a theorem of that, and it says that the altitude of the hypotenuse of the right triangle forms two triangles that are similar to each other and to the original triangle. So all three of those triangles are similar. And that's actually it for the first lesson in chapter 11. And now we'll get to the practice problems. So here's practice A. Okay, practice A says use proportions to find y in this. So here's a situation where we have this right triangle and we've used an altitude to split it into two smaller right triangles, and all three of those, remember, are going to be similar. So we look at y, and y is either going to be the small side of this big triangle, it's the smallest of triangle RST, or it's the hypotenuse of this little triangle RSP. So we need to figure out what proportion we want to set up where we could use that. So what you might want to do first is list what the triangles are. The big triangle is obviously RST. Okay, that's triangle RST. And RT is the hypotenuse, RS is the small, and ST is the medium. So let's look at the second one here. If we're looking at triangle SPT, okay, we know that the right angle was above the R, or the S, sorry. So we want the P, that's going to go with the S. And we went from small to large to hypotenuse. So we want to do that same thing with this triangle. So we're going to go from small, which is SP, to large, which is PT, and then the hypotenuse. So that's in that order. And that's also going to be similar to this triangle over here, where the small side is going to go from R to P to S. So you can kind of see what sides and what angles kind of go together. So now this is a little bit tricky, but we're going to try to set up these proportions to find out what y is. So if we look at the big triangle, we could say that y, that will be RS, is to RT. So RS is to RT, just like if you look at this one, RP is to RS. So those would be congruent. So let's look at those. RS is Y, is to RT. Our whole length of RT is 25. And then looking at RP, that's 9, is to RS. Well, that's Y again. So sometimes it's handy to use the y in both places that it occurs, because look what happens next. We do y times y by cross multiplying, we get y squared. And 9 times 25 is 225. To solve that, we take the square root, and we get that y equals 15. Now remember from algebra that the square root of 225 is actually plus or minus 15, but in this case it's only 15 because we can't have a negative length. So the length of y is 15, and that's the answer to practice A. Okay, here's practice B, and it says if CD, that's this length, is the same as DF, we need to find out what A is. Okay, this is actually a pretty tough problem. Let's see if we can work it through here. CD is the same as DF. That means that this is an isosceles triangle. And what we know about isosceles triangles is that the sides are the same, but also the base angles are the same. So if this one is 2b, b plus b would be 2b, this one also must be 2b. Alright, so we have this as being 2b, but now we have still a and b. We have two variables, two unknowns, so we're going to have two equations in order to solve that. So one of our equations, we could, well, there are a few different ways we could do it because we have a couple of triangles, but we could say that this 3a is an exterior angle to these two. You see that? How this 3a is the exterior angle. So 3a actually equals a plus b because the exterior angle is equal to the sum of the two remote interiors. And if we get all of our a's on the side, we know that 2a is the same as b. And that's a nice substitution that we have there. So we'll be able to use that to substitute. Then we could use for our second equation this triangle here, which that would be 3a plus b plus 2b, just using those angles from the triangle, and that will equal 180 degrees because it's a triangle. Like I said, there are a few ways you could do that, but that's one of them. Combining an like term, or actually, if I want to substitute here, now that we have an expression for what b is, we could use 2a, and we could say 3a plus 2a plus 2 times 2a. So that's again just substituting. Instead of b, we're going to write what b equals, which is 2a. We'll put that in there, and that should equal 180. Now we have it all in a's, which is what we're looking for. So we have 3a plus 2a plus 4a equals 180. That looks like 186. 180 is what that's supposed to be. Then we have 5, 9a equals 180. Divide by 9. And we find out that a is 20. And that's the answer to practice B. Okay, practice C says to find the perimeter of L, K, and Q. So it's that quadrilateral right here. And it tells us that LM, this whole distance here, is 18. And MQ is 10. And KN, this one, is 7. Alright, well if this thing is 18, then obviously these parts that are marked as equal would be 9 and 9 because they're marked as being the same. And we can figure out this one as well, that these must be 5 and 5. So you've almost got that perimeter. The perimeter will just be the sum of all of these added together. But we don't know what this LQ is quite yet. However, remember that when we have these two triangles that are similar, if it splits these so that they're proportional, like this is 9 to 18, this is 5 to 10, so this line that splits a triangle and makes those two segments proportional, then these are also parallel, and these are similar triangles. So if these are in the ratio of 9 to 18 or 1 to 2, then this must be in that ratio as well. So this would be in 7 to 14. So 14 must be that missing length there. And then to find the perimeter of LKNQ, we just add up all four sides, and when we add those up, we'll get 35, which is the answer to practice C. And finally, we have practice D. It says triangle JLN is similar to triangle RTV, and the ratio of each pair of corresponding sides is 2 to 3. So we know that the ratio of JLN to RTV is 2 to 3. The length of the altitude JLM is x minus 4, and the altitude TS is x minus 1. You'll probably remember that we talked in the last lesson about the altitudes also being proportional, just like the sides of the triangle. So we can complete the proportion by having LM. LM is on the top with this one, and that will be to x minus 1 on the bottom. That'll complete our ratio, our proportion, and then we can just cross multiply and solve. And we'll just cross, so sorry, I didn't cross multiply on that. Sorry, it got a little crazy here for a second. Alright, so we can just cross multiply, do 2 times x minus 1, and that'll equal 3 times x minus 4. So we have 2x minus 2 equals 3x minus 12. And when we solve that, it'll be easiest to move our x's over here, so we don't have a negative. Negative 2 equals x minus 12. If my thing will work. X minus 12. Oh dear. Okay, let's try that. 12? Come on, little computer. There we go. And then we'll add 12 to both sides, and we get x equals 10 for our solution. So the answer to practice D is x equals 10. And that wraps up practice 72.